Hello learners, welcome back to my channel Shraddha's Physics. In this lecture, we will discuss on the magnetic moment of the nucleus. So let us begin our topic, that is the magnetic moment of the nucleus. Basically, it is denoted as mu. This is your subscript L. Okay, this is your magnetic moment of the nucleus, that is mu L. A charged particle moving in a closed path, it produces a magnetic field. The spin angular momentum and the orbital angular momentum of the protons within the nucleus produces magnetic field, and this can be described in terms of the resultant magnetic dipole moment located at the center of the nucleus. Since here we are focusing on the nucleus, so in an atom the central part is called your nucleus, and inside this nucleus the neutrons as well as the protons are present. Neutrons carry no charge and proton carries positive charge. Okay. Now this proton, it possesses the two type of angular momentum. One is the orbital angular momentum because of its motion around the orbit, we can say, like as in the case of the electron, these electrons are revolving. This is suppose your nucleus, the electrons are revolving around this nucleus. Similarly, proton also has the property to revolve inside the nucleus. That means when it will revolve in a orbit, so for that it will possesses the orbital angular momentum. And when this is suppose your proton, it will spin about some axis passing through its center of mass, we can say this is your some axis passing through its center, then in that case we can say that it will possesses the spin angular momentum because of its spin, that is the spinning motion about its axis of the center of mass, it will possesses the spin angular momentum. And because of its orbital motion, that is the orbital motion, it will possesses the orbital angular momentum. So the spin angular momentum and the orbital angular momentum of the proton within the nucleus, it produces the magnetic field, and this can be described in terms of the resultant magnetic dipole moment located at the center of the nucleus. Since proton is a charged particle, or it carries the charge plus sign, that is their positive charge, since it is a charged particle, so when it will move in a closed orbit, then it will produce a magnetic field. So the current developed by the circulation of the proton having charge E, that is plus E, about the center of the nucleus with the frequency we can say nu in a circular loop, I can write I will be equal to E into nu. I will be equal to E into nu, and this nu, it can be represented as E into, in place of nu we can write 1 by T. So this will be E by T, where T is the time period. So the current will be equal to E by T. Now the orbital magnetic dipole moment means the moment of the proton. Okay, the magnetic dipole moment, it means the magnetic moment of the proton mu L. It can be written as mu L will be equal to I into A. Mu L will be equal to I into A, that is the current into area. Now in place of current we can write E by T, and in place of area I will write pi r square, and this is your r cap, it will show the direction. This r cap will show the direction of the magnetic dipole moment of, that is your mu L. So area is here pi r square into r cap. Since area for the circular loop will be pi r square, and this r cap, it represents the direction. So here A will be equal to area of the loop, and r is the radius of the loop, and this r cap represents the unit vector in the direction perpendicular to the plane of the loop. So finally the orbital magnetic dipole moment we get, this is equal to E by T into pi r square into r cap. If v is the velocity of the proton, then we can write T will be equal to 2 pi r by v. This T will be equal to 2 pi r by v. Now this equation mu L equal to E by T into pi r square into r cap. Now in place of T, if I will substitute 2 pi r by v, then this will be mu L will be equal to E divided by, this will be in place of T I have to write 2 pi r by v, or this will be simply EV by 2 pi r, this expression into pi r square r cap. Okay, So this is the value of mu L. And again, this R will get cancelled with this R, and this will be pi get cancelled with this pi. So this will be EVR by 2 into R cap. This is your magnetic dipole moment. If I will multiply MP in the denominator and the numerator, then this will be equal to, in place of MVR, I can substitute L. This L is the angular momentum of the proton. This is your angular momentum of the proton. So mu L will be equal to EL divided by 2 MP into R cap. In place of MVR, simply we are substituting L. That is the angular momentum of the proton. So finally, this mu L equal to EL vector divided by 2 MP. This L R cap, it will simply written as EL vector. So mu L vector will be equal to EL vector divided by 2 MP. Now, if we will put L equal to H cut in this expression, that is mu L equal to EL by 2 MP, then this will be EH cut by 2 MP. This mu L will be equal to EH cut by 2 MP. Now, this expression, this is the important expression. In place of L, simply if I will write mu N, then this will be EH, this equal to, if I will write mu N, capital N, this will be equal to EH cut by 2 MP. It can be denoted like this, mu N, and that is called the nuclear magneton. This is important. This is called the nuclear magneton, and its value is EH bar by 2 MP. You know H bar equal to H by 2 pi. Okay. So this is called, this mu N is the nuclear magneton, and that is the magnetic dipole moment associated with the spinning proton. That is, when the proton will spin about its axis, then the magnetic dipole moment will be equal to EH bar by 2 MP. And if you substitute all this value, that is E is your constant, that is 1.6 into 10 power minus 19 coulomb, into this H bar value is 6.58 into 10 power minus 16 electron volt, divided by this 2 into the mass of the proton, you know, 1.673 into 10 power minus 27 kg. So after calculation, you will get 3.15 into 10 power minus 8 electron volt per Tesla, or that can be also written as 5.05 into 10 power minus 27 joule per Tesla. Now similarly, we can write the magnetic dipole moment associated with the spinning electron. As in this case, we are writing the expression for the magnetic dipole moment associated with the spinning proton. So here also we can write the magnetic dipole moment associated with the spinning electron. We can write this will be mu B equal to EH bar divided by 2 Me, and this is called the Bohr magneton. So you can see here the expressions are same here. That is, our general expression is mu equal to EH bar divided by 2 MP, and here simply this mu substitute is your B, that is for the Bohr magneton, that is equal to EH cut divided by 2 Me. This Me represents the rest mass of the electron. Okay, this represents the rest mass of the electron. So mu B is the Bohr magneton, and its value can be written as 9.27 into 10 power minus 24 joule per Tesla. Okay, simply if you will substitute the value of EH bar and Me, that is the mass of the electron, 9.1 into 10 power minus 31 kg, like this. Here we have also substituted the value for the mass of the proton. Simply if I will substitute all these values, so we will get 9.27 into 10 power minus 24 joule per Tesla. Now we know mass of the proton MP will be equal to 1836 times Me. Since here you can see mu is inversely proportional to the mass, so here for the nuclear magneton, if I will write this is the nuclear magneton, and if I will take the Bohr magneton ratio, then this will be simply equal to, the mu is inversely proportional to the M. So here I will write, this is your suppose 1 by, for the nuclear magneton this will be MP, and for the Bohr magneton this will be Me, because here this is inversely proportional. So now we can write mu N by mu B will be equal to Me by MP. Okay, so from this relation I can write, from this relation Me divided by MP, that will be equal to 1 by 1836. So this is, so the ratio between mu n and mu b, that is the nuclear magneton. Just a minute. The nuclear magneton and the Bohr magneton, that will be equal to the mass of the electron divided by the mass of the proton, and that is equal to 1 by 1836. Okay. Now for all the nuclei, the magnetic moment can be written as, this is simply G into EH bar divided by 2mp. Okay, this mu in general form can be written as mu L equal to some G into EH bar divided by 2mp. So you know this EH bar by 2mp is nothing but your mu n, that is the nuclear magneton. What is this G? So this G factor, it varies from nucleus to nucleus. That is, if we will consider the proton, then this G value will be equal to 2.792, and if we will consider for the neutron, then this will be equal to minus 1.913. Okay, so now for the for the proton, this is equal to 2.792 times EH bar by 2mp, or we can write it as, this will be equal to 2.792 into mu n. And similarly for the neutron, that is mu neutron equal to minus 1.913 into EH bar by 2mp. Since this EH bar by 2mp is your mu n, that is the nuclear magneton, so this will be simply minus 1.913 into mu n. So these are your some important relation for the proton and neutron. This is also important, that is the G factor. It is 2.792 for proton and minus 1.913 for the neutron. So this is all about your magnetic moment of the nucleus. So this is all for today. If you have any doubt, can ask me in the comment section. Thank you all.